Well, hello everybody, Dave here, and today we do our second lesson in thermodynamics, focusing on energy transfer and thermodynamic processes. We will specifically focus on ideal gases as a means to simplify this discussion. So to start our discussion of energy transfer, we have to remind ourselves of the difference between the definition of heat and the definition of temperature. You'll remember from last lesson that we were able to find an equation for temperature that is related to the average kinetic energy of the motion of molecules itself. This is different from heat, which is representing the total kinetic energy, or more specifically, the flow of energy from an object of higher temperature to an object of a lower temperature until thermal equilibrium is reached. Now, this energy transfer can be done by three primary ways. The first is this idea of convection, and this is the idea of taking a fluid, and this could be a gas or this could be a liquid, and the churning of the fluid allows the energy to transfer from one location to another, but in this case the material itself has to move. With radiation, there is no material because the energy actually moves by electromagnetic waves. This is the primary way that our sun sends energy from itself to here. Now, an ideal body is one that can absorb and emit all of this radiation, and we call this a black body. Now, the equation that you see before you is called Stefan's law, or Stefan-Boltzmann's law, and this is the actual rate at which an object can emit this energy, and it's epsilon sigma at to the 4. Now, this constant epsilon is known as emissivity, and emissivity is the ability to actually emit this energy. And so if we're talking about something like a black body, it has an emissivity of 1. A is the surface area, T is the surface temperature, and sigma is known as Stefan-Boltzmann's constant, which is the value you see before you. So for anybody that's looking into something like astrophysics, this is certainly an equation that you'll see a lot. For the sake of our discussion, though, we're going to focus on the idea of conduction. And conduction is when collisions take place between two substances, and there is this energy transfer because of these collisions. And you see before you this equation now, which is the rate at which the energy is transferred when there is conduction taking place. You can see the diagram in the bottom right that there is a hot object, there is some material that allows this transfer to take place, and then you have the cold material on the right hand side. It is a law of thermodynamics that heat only transfers from hot objects to cold objects. So with this equation we can see that we have K, which is now thermal conductivity. It's just the ability for this particular material to conduct energy from the hot object to the cold object. A is our cross-sectional area that's in connection to the cold object. And then we have L, which is the thickness of the slab, or just the thickness at which the energy itself has to transfer through. So again, it's important to recognize that this is a rate of energy transfer. So with this understanding, let's consider a situation where we have a cylinder and a piston. And inside the cylinder, we're going to have a gas. Now, as we move the piston down, there's going to be work that's being done on the gas because we're compressing it. Well, this work is the exact same kind of work that we've dealt with in the past as being the applied force times the distance traveled. Well, in this case, we're going to relate force to pressure, and understanding that pressure is equal to force per unit area, and the distance traveled in our case is delta y. Well, the cross-sectional area times this height is actually just the change in volume of the cylinder itself. So what we end up with for an equation for work is negative P delta V. Now this negative sign is a hardwired negative because we want to make sure that whenever we talk about work being done on the gas, that we understand that when a volume is being decreased, that there has to be work done on the gas to make that happen. When the gas naturally expands, then there should be negative work being done on the gas because we understand this to be what it wanted to do anyway. But if we related that to the work being done on the environment by the gas, then this would actually be positive work done. So one of the hardest parts of this unit is to understand this negative sign and the language of the question and what it represents. So the word by and on are absolutely essential in getting the sign correct for the mathematics involved. One of the best ways that we can understand this energy transfer is to create a PV diagram. On the bottom right, you see a graph of pressure as a function of volume. And what we have is the process of transferring energy from state I to state F. So in this case, you can see that the pressure remained the same, but the volume went from a larger number to a smaller number. So this, in fact, represents a compression of a gas given a constant pressure. Now, if we take a look at the area underneath this line, we can see that we would have pressure on the vertical times the change in volume on the horizontal. Well, that's really just our equation for work. The thing that we have to watch out for with this calculation, however, is there's no hardwired negative sign in this calculation for work. So you're going to have to understand that because there's a compression of volume occurring, this is going to represent positive work being done on the gas. If the volume were the opposite way and it was going from a smaller volume to a larger volume, now we'd be dealing with an expansion of the gas, which is a natural thing for it, which means it would be negative work being done on the gas. So again, this negative sign convention is going to be exceptionally challenging to understand at the beginning, and even more challenging to actually keep track of through the course of your problem solving. So let's do an example that applies this concept. We're going to create a PV diagram based upon the scenarios that you see below. With part A, we're going to take a gas and we're going to expand it from a volume of 1 liter to 3 liters at a constant pressure of 3 atmospheres. Well, the first thing I hope that you see is that there's a unit issue that we have to deal with. When we're calculating work, we have to maintain SI units, which means pressure needs to be in pascals and volume needs to be in meters cubed. So once we do those conversions, we can calculate the magnitude of 600 joules. This is where understanding what's happening to the gas is essential, as well as understanding which work are we trying to find. In this case, we see that a volume is expanding and we're trying to find the work being done on the gas. So because the volume is expanding and the work is being done on the gas, we're talking about a negative work being done on the gas. There would be a positive amount of work being done by the gas if we were considering the effects of the gas on the environment itself. But in this case, we are focused on the work being done on the gas. So in this case, because it's an expansion, it has to be negative. With part B now, we're going to take this gas and we're going to cool it at a constant volume until the pressure falls to 2 atmospheres. Now, this is a bit of a trick because if you see on the PV diagram, this is a vertical line. Well, with a vertical line, there is no area, which means there shouldn't be any work done. And that should make sense if we take a look at our equation for work and understand that there is no change in volume. We have maintained the volume and all we have done is change the pressure. And so in this case, the work being done is 0. So if you take a look at the diagram on the right, you can see this horizontal line that's pointing to the right, representing an increase in volume. And then you see this vertical line pointing straight down, representing this cooling process by which we are now changing the pressure. Part C now is going to be to take this gas and compress it at a constant pressure of 2 atmospheres from 3 liters to 1 liter. Again, we have to do a unit conversion, and we have to recognize that this would actually end up as a negative value. However, we know that in the process of compressing the gas from a higher volume to a lower volume, there has to be a positive amount of work being done on the gas. So the result, even though it would have ended up as a negative value for me, I'm still going to eliminate that negative sign to represent a positive work being done. With D, again, we're going to take this gas at 2 atmospheres, we're going to increase it to 3 atmospheres, and we're going to keep this at a constant volume. Well, this is just like part B, where no work is being done in the process because there is no volume change. And because of that, the work being done is 0. So you can see again that what we have is a rectangle with 2 vertical lines, 2 horizontal lines, and the arrows in the direction that they point is absolutely essential because this is representing the processes in order of how they occur. So if we want to find the net work that has been done on the gas, we simply have to add up the work being done through this entire cycle. Now, assumptions may be that this should end up being a 0 sum, but the thing that you have to remember is that work is actually path dependent. And in this case, there was more negative work being done to expand the gas than there was to compress the gas because of the pressure differential. And so you can see that inside the rectangle, I've shaded this area because that's actually the magnitude of the net work done. The sign is associated again with understanding the processes that occurred. The fact that expansion had a higher magnitude than compression, we should end up with this negative value. So this path dependence in the case of thermodynamics is due to the fact that there are two quantities that this energy is being converted into. We have the quantity Q, which is heat, and then we have this other quantity, which is the internal energy of the gas, which is labeled by U. So you can probably see that we've already focused on pressure and volume as a couple of variables that we focus on when determining the processes that occur. Well, in general, we determined in a previous lesson that we have an equation of state for an ideal gas that is PV equals nRT. And what that means is if we are looking at a gas, there are these state variables that we have to focus on when discussing the thermodynamic processes. In this case, P, T, V, N, and U, where U again is the internal energy. The important thing to recognize is when we're dealing with heat and work, we're not talking about a state variable. We're actually talking about the method by which the state has been changed from one state to another. And so whenever you see a state variable collection, what they're trying to show you is here's the initial states in terms of pressure, temperature, volume, number of moles, and internal energy. And then after some process, either Q or W, here is the new state of that gas in terms of the same variables. And based upon those changes, we can begin to discuss the processes that allowed us to get to that state. So you've probably noticed in the last couple of lessons that we've really focused on internal energy. We were able to define it in terms of the macroscopic quantities, specifically temperature, and we were able to define it in terms of the motion of the particles itself and the kinetic energy involved. So when we're talking about internal energy, we're really talking about the potential and kinetic energy associated inside the object itself. And the question becomes, how do we increase this particular value? Well, if we take a rubber ball, for example, the first thing we could do is we could squeeze it and throw it against the wall. And what's going to happen is if you feel that ball, it's going to heat up. And that's because there's work being done on the ball. So energy is being imparted on the object to increase its internal energy. At the same time, if you leave a rubber ball out in the sun for a while, you know that it's going to get hotter because there's heat flowing into the ball. So you'll notice in both cases, there's work being done on the ball. There's heat being transferred into the ball. So there's actually two methods by which we can change the internal energy of the system. So to summarize this then, we have that our change in internal energy is equivalent to the heat being added to the object and the work being done on the object itself. And we have what is known as the first law of thermodynamics. And so when we take a look at this equation, it is simplistic in its structure, but the applications of it are very wide-reaching. So it's important, again, to understand the negative sign convention and how this applies to the first law of thermodynamics. So we have three variables here, Q, W, and our change in internal energy. Well, if we have a positive quantity of Q, that means that heat is flowing into the system. If we have a positive value of work, that means that work is being done on the system. This is exactly like what we did in our example. If we have a negative value of heat, that means that heat is being extracted from the system or it's flowing out of it. And if we have a negative quantity of work, that means that the work is being done by the system or negative work is being done on the system. Well, you can see that if we have a positive change in internal energy, that just straight up means that it is increasing. And if it's negative, it's decreasing. So this table here is something that you absolutely want to memorize, because if you don't use these appropriately, you can tell that with this simplistic equation, we're going to get wildly different magnitudes of the change in internal energy when we start to play with it. When we deal with this law, we're going to really focus on scenarios that involve gas in a cylinder, and then we're going to take a piston and we're going to compress it, or we're going to attach it to some sort of heat source so that we can increase the temperature of the gas, which will increase the volume, and that piston will move. And so you'll notice that in our next slides, we're really going to focus on this cylinder and the gas inside. So let's remind ourselves that the internal energy for monatomic gas is U is equal to 3/2 nRT, where N is the number of moles, R is the universal gas constant, and T is the temperature in Kelvin. Now, if we want to talk about the change in internal energy, we need to redefine this in terms of this new quantity called the molar specific heat at constant volume. And so we get this equation that delta U is equal to NCV delta T. Well, what we've done is we've taken CV to be equal to 3/2 R for a monatomic gas. If we want to expand this to a diatomic gas, we have to discuss this in terms of degrees of freedom. And basically what happens is with a monatomic gas, there's only 3 directions that it can spin. However, with a diatomic gas, there's also this ability for it to tumble. We don't necessarily focus on its ability to spin on the long axis, but it can certainly tumble in 2 different directions, which gives it this additional 2 times freedom of motion. Hence the 5/2 r for the constant. So this may start sounding really complex. We're talking about tumbling of particles. We're talking about degrees of freedom. And to be honest, at a higher level, thermodynamics has a statistical component which makes it exceptionally challenging. For the sake of this course, though, we're going to focus on the 4 most common processes and how they affect an ideal gas. And so the list of the 4 processes below are the most common processes that we deal with. And you'll notice that I've listed the laws that we talked about in the first lesson, and that's because if you go back and look, this is exactly what we did. We kept the temperature constant to determine Boyle's law, the pressure constant to determine Charles' law, and the volume constant to determine the Gay-Lussac law. Well, you can see that we have names for this: isothermal, isobaric, and isovolumetric. Keep in mind that with volume, you can also call it isochoric. Well, when we create PV diagrams to represent these processes, we're going to refer to them as isotherms, isobars, and isochores. So when you read a problem, if you see those statements being made, that's exactly what they mean, is the PV diagram of that process. There is this 4th process, however, which I haven't associated with any law, and this is the idea of an adiabatic process. And what we're going to do is we're going to take a cylinder, we're going to isolate it and insulate it from the environment so that no energy leaves or enters the system by heat. And so when we do that using the first law of thermodynamics, that means that Q in this case is going to be equal to 0. And it's a little more challenging because as we get into the discussion, it sounds a lot like an isothermal process, and as you'll find out, that's just simply not the case. So let's begin our discussion of an isobaric process. In the top left, you'll see a cylinder with a piston in it, and to the left of that cylinder there is a heat source that is allowing energy to flow into the gas. The result of this energy is going to be a volume expansion. Well, as the volume expands, the piston itself is going to move. Depending upon how we discuss this, this is either going to be a positive amount of work done by the system on the environment or a negative amount of work being done on the system. The question becomes then, how is this work done? Well, because there is this change in internal energy that's taking place as well. And so I've given you the derived equation for the change in internal energy. If we take a look at the ideal gas law, we can solve this for an isobaric process by first recognizing that the 2 things that are changing are volume and temperature. And so P delta V is equal to NR delta T. You may recognize this P delta V as the amount of work being done. So if we take the first law and solve for Q, we can determine that Q is equal to delta U minus W. But in the case of the work being done on the gas, we have to refer to it as delta U plus P delta V. So remember, with the first law, you are always relative to the work being done on the gas. Well, we have this equation now for work as NR delta T. We have our original equation for the change in internal energy in terms of N and R. And combining these 2 quantities together, what we get is that the heat added to the system is equal to 5/2 NR delta T. Well, we can rewrite this if we make a new definition of a molar heat capacity, but in this case we're going to call it the molar heat capacity at constant pressure. And so we can actually relate that to the molar heat capacity at constant volume with the equation given below. There is a huge statistical component involved with this discussion again, which we're just going to leave for now. So Q is equal to NCP delta T is the equation that you would use to find the energy transferred by heat into the system when the process is isobaric. And so on the bottom left, you see our PV diagram. Again, we're representing the area underneath. We're showing the arrow pointing to the right, showing that we are going from a smaller volume to a larger volume. If we were to determine the work based on area underneath the graph, we would have to hardwire in a negative sign at the end because, again, the work being done on the gas is negative. So the next process we'll look at is an adiabatic process. And what we're going to do this time is we're going to put an insulator around the cylinder so that there can be no heat exchange with the environment and the gas. Because of this, the only way that the gas can expand in volume is by work being done on the gas. And so we can simplify our first law of thermodynamics to be the change in internal energy is equal to the work alone. So how do we calculate the work being done? Well, we already have our equation for our change in internal energy. That's 3/2 nR delta T. The thing that we have to remember, though, is when we calculate that, the work being done on the gas has to be negative, and that's because the kinetic energy is being transferred from the gas molecules to the moving piston. So this idea of the macroscopic energy associated with the gas itself is now being transferred to the movement of the piston. Now, if you take a look at the bottom left, you can see that we have this PV diagram of an adiabat. And what you see is two things. First, it's curved. And second, it is very steeply curved. And this is going to be the signature that we're going to be able to tell the difference between an adiabatic process and an isothermal process. And that's because this happens so quickly. Well, we have an equation that we could actually use to describe this curve, and this is PV to the power of gamma is equal to a constant, where gamma is actually the ratio of the molar heat capacity with a constant pressure divided by the molar heat capacity with a constant volume. So next up is this isovolumetric process. You will also hear this called an isochoric process, so please recognize that really there's two terms that describe the same thing. If you take a look at the PV diagram, you see that this is the vertical line that we were talking about previously. And we know that if the area under a PV diagram curve should represent the work being done, if there is no area, as this vertical line has none of, then there should be no work being done. Well, if we take a look at our equation for work, we can see that with P delta V, if there is no delta V, there can't be any work done, which means based upon the first law of thermodynamics, the only way to change the internal energy of the system, that is isochoric process, is with heat being added. And so what you see in the bottom left is this cylinder, but what we've done is we've fixed the piston in place so that the volume doesn't change when we add heat to the system. Well, what that means then is that our change in internal energy is equivalent to the heat being added, which is equivalent to NCV delta T. So you can begin to see now how our understanding of internal energy and the fact that when we're talking about the first law of thermodynamics, this is really what we're discussing is what is happening to the internal energy and why is it happening. This is the essential element that we have to understand to really get a sense of what's going on with these thermodynamic processes. So the last process we're going to talk about is an isothermal process. And this is where we're going to keep the temperature constant. Now that seems intuitively challenging because how do we keep the temperature constant while there is this obvious change in the system itself? And what we do is we take the cylinder and we attach it to a heat reservoir or an energy reservoir. And what that means is that we attach it to some heat source that has such a high specific heat capacity, or it is so large that the actual energy exchange itself won't change the temperature of the reservoir. Well, because of this, we know that this allows for a constant temperature to be reached so long as we maintain this energy transfer nice and slow. This is a lot different from an adiabatic process where we do everything exceptionally quick. So based upon this slow change, based upon its connection to an energy reservoir, we know that with no change in temperature, there can't be a change in internal energy. This is based upon our definition of internal energy that we've already derived. Well, what that means is that the first law of thermodynamics just simplifies to the work being done on the gas has to be equivalent to the negative heat being added to the system. And so if we take a look at the PV diagram, you can see that this is again curved. So the question becomes, how do we tell the difference between this curve and a different curve? Well, the first thing we do is we recognize that this is all bound by the ideal gas law. And if we solve for P, what we see is we have nRT divided by V. Well, we know that N, R, and T are all constant, which means that to find what the work is, we would have to calculate P delta V. Well, this isn't done easily when it's a curved process, so what we would actually have to do is some calculus, and you integrate P with respect to V. I'll save you the hassle, and I'll get to the point that the work being done on the gas is equal to negative nRT times the natural log of the final volume divided by the initial volume. Now, that negative is important because this is the work being done on the gas. Remember, we are allowing the gas to expand, which means the work being done on the gas has to be negative. Well, what that means is when we apply it to the first law, the amount of heat being added to the system has to be the positive amount of this quantity, and so we get our equation of Q is equal to nRT times the natural log of Vf over Vi. I've given a note at the bottom of the screen just to show you that there are different versions of this equation that you'll see online, and that's all based upon how they deal with the integral and how they deal with the negative sign itself. And so there are little mathematical tricks that allow us to write this a little differently. I'm just going by the most straightforward simplistic view, but by all means you're more than welcome to use a different version so long as it is based upon the work being done on the gas. Now, the big question that everybody likes to ask is, what's the difference between an adiabatic process and an isothermal process, and how do we tell the difference? Well, I've given you a nice little list there to sum up the differences between the two. When we're dealing with an adiabat, we're talking about something that happens quick and there is no heat transfer. That's our key right there. I've given you the equation that shows you that the pressure is proportional to V to the power of negative gamma, and that's because it's an inverse relationship, and this power, remember, was associated to CV and CP. With an isothermal process, we are doing it nice and slow, and we are exchanging heat into the system by way of some sort of energy reservoir. And if you take a look at our equation that we derived for pressure, we know that it's proportional to volume to the power of -1. And so to summarize today's lesson, really what we've done is we've learned the first law of thermodynamics. And we've recognized the fact that the two processes by which we can change the internal energy of a system is to either add heat to the system or to do work to the system. And what I've done for you is on the bottom, I've given you a table that summarizes the processes and how to calculate each of the quantities associated with the first law. I've also given you this diagram in the top right that shows you on a PV diagram what each process looks like. I especially want to point out that when we look at the adiabat, you'll notice that it looks like it's going from one temperature to another in a steeper curve, and that's because if you take a look at the adiabatic process, we can see that the only quantity that's being calculated is based upon the change in temperature. So one of the nice signatures of an adiabat, if you have multiple isotherms on your PV diagram, is this seeming connection between one isothermal and another. So I hope that some of this made sense to you today. Good luck with your practice problems. Again, watch out for that sign convention. Make sure you recognize that everything is being done on the gas versus by the gas. Best of luck, everybody. We'll see you again.